our presentation on the use of deep reinforcement learning for mitigating cyber-physical DER voltage unbalance attacks. Our work was a collaboration between Lawrence Berkeley National Lab and Arizona State University. This work was carried out in the backdrop of increasing deployment of customer-owned DER on distribution systems. These devices are now being deployed with advanced control functionality recently codified in standards such as IEEE 1547 or California Rule 21. While historically, these devices operated as fixed power injections, they are now set to become actively controlled devices that will modulate their power injections in response to system conditions. Of particular interest in this work will be their volt var and volt watt functionality, intended to ensure that system voltages remain within allowable limits. The deployment of these devices introduces an entirely new attack vector from the perspective of cyber-physical security. Unlike typical voltage regulation equipment, DER are typically neither utility-owned nor directly controlled. Instead, large populations of the devices are either controllable or accessible by a small number of manufacturers and/or aggregators. Furthermore, these communication links are typically less secure, which makes ensuring the integrity of commands more difficult. DER, volt var, and volt watt are typically piecewise continuous functions that determine active and reactive power set points as a function of locally measured voltages. Within this work, we confine ourselves to functions parameterized by 5 breakpoints, ADA, shown here. The attack considered is where an adversary will gain control to a subset of network single-phase DER and translate these curves on a per-phase basis to create a large voltage imbalance. That it may cause DER on one phase to inject reactive power to increase the voltage on that phase while consuming reactive power on the remaining 2 phases to lower their voltages. Therefore, the research objective in this work will be to develop a local supervisory controller that resides locally on uncompromised DER and adaptively reconfigures volt var and volt watt functions to minimize voltage imbalance. A critical feature of the proposed controller is that it should not inhibit normal DER operation. Example, response to false. Within this work, we explored the use of deep reinforcement learning to learn this supervisory controller. This is a model-free approach where deep reinforcement learning models the controller as a neural network and seeks to learn an optimal policy that is a state to action mapping by repeatedly interacting with an environment. Each environment interaction receives a reward R, which is a measure of performance. The agent performs gradient-based optimization on its neural network to maximize its received reward. The most common approach is to perform gradient ascent on the expected return. This, however, has a drawback of high variance. To counteract this, actor-critic methods, where we train a critic model that approximates the value function. Therefore, given a policy pi parameterized by theta and a value function v parameterized by v, policy gradient performs stochastic gradient optimization on the objective shown here, where A, the advantage function estimation, is a measure of how much better it is to take a specific action compared to the expected return at the given state. Training of actor-critic methods, however, can be unstable when the data distribution changes due to large policy updates. To address this, we use proximal policy optimization within this work. PPO uses a clipped surrogate objective shown here to encourage more gradual updates to the policy rather than large changes. This approach builds upon trust region methods and introduces a clip term parameterized by epsilon that restricts policy updates. Our representation of DER consists of a low-pass filter for the voltage before it is passed into the volt, watt, and volt bar control functions. These functions then determine active and reactive power set points respectively. These set points themselves are then low-pass filtered to limit the ramp rate injection of active and reactive power into the grid. The time constants of all the filters are random among devices to ensure heterogeneity. The goal of the supervisory controller is to adaptively reconfigure these control functions, shown here within the blue box, to mitigate adverse system conditions. As opposed to allowing the supervisory controller to independently optimize over each breakpoint of the control function independently, we allow the agent to translate the curve from its default parameterization. Translating these curves has the effect of indirectly controlling the active and reactive power injections onto the grid. An additional advantage of formulating the agent action in this manner is that the agent can easily reset back to its default parameterizations once the attack has been removed. These default parameterizations are assumed to have been determined by some other controller and correspond to some optimal behavior during normal operations. The observation input vector to the agent consists of 4 components. The first is a measure of local voltage imbalance. The second component are the locally measured 3-phase voltages. For the case of single-phase DER, this will require some local communication among neighbors, given that each DER can only measure the voltage on one phase. The third component, the available reactive power capacity without active power curtailment, allows the agent to more accurately learn the mapping between the action taken and the change in system conditions. The same action taken in the morning when there is a lot of reactive power capacity due to low solar irradiance versus noon when there is low reactive power capacity will result in different system responses. The final component in the observation vector is the previous action taken by the agent for each phase. This is included to help the agent minimize the total number of control actions it takes. The reward function consists of 4 components. The first component seeks to minimize voltage imbalance and is the main term. The second term seeks to encourage the agent to minimize the total number of reconfigurations. The third component encourages the agent to stay as close to its default parameterization as possible, assuming that these default parameterizations correspond to some optimal operating point. This penalty also implicitly penalizes the agent for taking an action that results in poor system voltages. The final component punishes the agent for any active power curtailment as a result of the action taken. We conduct our training in a Python environment using OpenDSS as a power flow solver and RLlib to manage the deep reinforcement learning side of things. In order to keep the training tractable, we consider a single RL agent whose observation input vector is from the node with the worst case voltage imbalance. The corresponding output action is then applied across all single phase DER inverters on the system. Once the optimal policy has been trained, this policy will then be deployed locally on DER and act only on local measurements. This figure shows a base case condition with no defense where an adversary has gained access to a subset of DER on the network. We see that at a time t equals 200, the adversary maliciously reconfigures the DER control logic to cause a large voltage imbalance on the network. In the second subplot, we see a measure of this imbalance, which peaks around 4%. The third subplot shows no action taken by the uncompromised inverters, and the final plot shows the action of the substation tap changing transformer. For the case of active defense, however, we see that the agent quickly takes an action once it has detected an abnormal imbalance. We see this in the third subplot, which shows the action taken by all agents on the network. This action successfully reduces the voltage imbalance to under 2%. Looking at the action of the agents, we see that at around 320 seconds, some of the agents on phase B take a different action than the rest. This can be attributed to natural load variations leading to a slightly different local observation vector for each agent. For the case of a more severe attack, where 40% of the DER is compromised, we see similar behavior from the agent. That is, the agent detects the imbalance and takes an action to reduce the imbalance. This particular attack was carried out in the middle of the day when the agent had minimal available headroom for reactive power capacity. If we look at the same attack in the morning, however, we see very different behavior. In this case, there is a lot more available headroom for reactive power control as the solar irradiance is lower. We see the distributed agents exhibiting oscillation behavior in their output action head. This kind of behavior was not present during training due to the training structure employed. As previously explained, during training, we train a single agent and apply the same action across all inverters. However, when deployed in a distributed manner, each agent can have a different observation vector that can cause unusual behavior. Within this work, we showed how deep reinforcement learning can successfully learn an optimal policy that reconfigures the ER control logic to minimize voltage imbalance. Some of our future work includes expanding the library of ThA, more sophisticated training regimes, and understanding the sensitivity of the agent to specific networks. Thank you.